We are very happy to have Derek Teany from Stony Brook University giving the ICFE series seminar on the critical point, soft pions in heavy ion collision. Please, Derek.
Okay, so, whoops. Okay, now you have this tab in front of you. Okay, maybe it'll go away. Shit, now it's frozen. Okay, 1 second. There we go. All right. All right. Okay, so nice to see all of you. Okay, so this is work done in collaboration with a bunch of people. Eduardo Grossi, who's here. Alexander Soloviev is here. My student, Franklita Yan. Juan Torres, who's a postdoc in Frankfurt. Okay, so let me just talk about the motivation quickly for this this work. Okay, the first paper appeared here. There's a couple more work in progress. Okay, and I'll try and review all that. Okay, so the first part of the talk will be about hydrodynamics in the chiral limit. Okay, so we sort of think that chiral symmetry and chiral symmetry breaking is an important part of QCD, and yet, if you look at the general theory of heavy ion collisions, you know, chiral symmetry, let's face it, plays no role in the current model of heavy ion collisions. It's the standard model involving hydrodynamics and so forth. Chiral symmetry breaking essentially is irrelevant, okay? And, you know, that seems like a problem to me, okay, or at least something that could be improved. And nevertheless, and there's reasons to think that you should try and improve it. So if I look at the real world QCD, which let's take lattice QCD, okay, and there's a lot of evidence of chiral symmetry breaking and the O4 scaling associated with this, with the pattern of symmetry breaking, okay? And so just to give an example, okay, so this is chiral symmetry in real QCD. So this is lattice QCD calculations by the hot QCD collaboration. They look at the chiral susceptibility, which is here, right? Well, okay, and they actually plot the chiral susceptibility as a function of temperature and quark mass, okay? So they actually start out at the above the physical point, right? That's where the pion mass is 160 MeV. Then they go down to 140 MeV, the physical point, okay? And then they decrease the quark mass further, okay, to where the pion is 55 MeV. And you see how the chiral susceptibility increases as they lower the quark mass, okay? And good. So the chiral susceptibility in O4 scaling, you know, near an O4 critical point, has very definite predictions for how this quantity should change as you change the quark mass. Okay, so it depends on you know, temperature in a very specific way. It depends on the quark mass in a very specific way, and basically the features that one is seeing in these curves, okay, are, I won't, you know, I'm not going to, it's not the purpose of the talk to say how well it's reproduced, but there's a lot of evidence, you can read this hot QCD paper, that many of the features that you see about the critical point are reflecting the O4 scaling properties of the underlying theory, okay? So the real world, okay, as measured by lattice, okay, knows about the critical point, right? Knows about the O4 critical point, yet, right, it plays no role in heavy ion collisions, okay? Seems like a problem, okay? And so I will sort of mention a little bit, well, okay, so we're gonna try and incorporate sort of chiral symmetry and chiral symmetry breaking into the hydrodynamic model, which has become a kind of standard model of heavy ion collisions, okay? Okay, so let's talk about O4 critical, well, not the critical point, so I'm not gonna really talk about the critical point. I'm gonna approach the critical point, but not really go through it yet. Okay, So let's talk about QCD and the chiral limit. Okay. So there's a bunch of conserved quantities. There's this stress tensor, baryon number, the isovector charge, the isoaxial vector charge. Okay. So here's the isoaxial axial charge. So the most important thing to get, first of all, is that there's a hat. Okay. So J hat is the isoaxial vector charge. Okay. So every time you see a hat, it refers to the axial vector charge. Okay. That's like, and if you see mu hat, that's the isoaxial vector chemical potential, and so forth. Okay, so every time you see hat, it's axial. Okay, and so in addition to these conserved quantities, there's, if you talk about the long distance parameters that make up the hydrodynamic theory, there is the phase of the chiral condensate, which we call the pion. So the pion is the phase, or the soft pions are the phase of the chiral condensate. Okay, right. So U, which is typically used in chiral perturbation theory, is parameterized by the phase of the pion. Okay, so the pion field, phi A, right, is just like the temperature and flow velocity, the isochemical potential, and the axial chemical potential, and it should be included in the constitutive relations of hydrodynamics. Okay, when you write it down. Okay. Further, you should include, in the real world, there's a mass term. Okay. And so because of the mass term, this axial vector charge will not be precisely conserved, and the pion field will decay at large distances. Okay. And so that's very important in the real world. So how large is the mass is very, very important. Okay. But nevertheless, in the strictly chiral limit, you would need to, this pion would never decay, the axial vector charge would be precisely conserved, and you would need to write down a theory which incorporates these Goldstone bosons into the hydrodynamic theory. And it's sort of analogous to a superfluid theory. So the superfluid U1 superfluid theory has a broken U1, and here you have a broken SU2 cross U2, and the appropriate theory is not hydrodynamics, but kind of superfluid hydro. Okay, so I'm going to kind of review a little bit what was said a long time ago by Son. It has only a few citations, sort of 10, right? But it was a beautiful paper where he sort of wrote down these hydrodynamic equations. Okay. Okay, so we want to, now in the real world we have a mass, okay? So of course, at very long distances, right, we don't have superfluid hydro, but regular old hydro, okay? So that's what I'm drawing here, these modes, which are K. Those are regular hydrodynamic modes. Now, if we have modes which have wavelength of order m pi, okay, these are the green one that I'm showing here, okay? Those would be kind of the superfluid modes that I'm talking about. And finally, we have modes where of order pi t, or the typical momentum in plasma, and these modes have, I'll call it hard modes. Okay? And we're going to be working in a regime where the fluid modes are the longest, the pion modes are the next longest, and the hard modes are the shortest. Okay. So now a natural question would be, how do these sort of superfluid Goldstone-like modes contribute, right, to the pressure and shear viscosity, the fusion rate of long wavelength modes, these black modes? Okay, so that's the kind of question we're going to be calculating. We're going to calculate it in detail. We're going to show how the superfluid theory can be used to calculate corrections to the pressure and shear viscosity. Okay, so now let's just talk here, like how good is this approximation? You know, m pi is kind of the same order of magnitude as the temperature, right? So how good is this kind of sequence of inequalities? Actually, I think it's quite good indeed, right? So if you look at real heavy ion collisions, okay, the typical momentum of a pion is like, or a hard particle is like 500 MeV, 500, 600 MeV now at the LHC, right? And if you look at the pion mass, 140 MeV, it's usually so small, like people don't even plot that bin, okay? So, and typically, if you look at the corrections, they come squared, right? So it's kind of 1/5 squared is the correction. So if I were estimating, how good is this approximation scheme that I'm going to be using, okay, it's sort of at least as good, better than 10%, okay? That would be my guess. All right, so that's going to be sort of the scheme that we're going to be talking about. Questions on that? Okay. So although the typical momentum is 500 MeV, the pion mass is 140 MeV, the corrections typically come squared. So I would guess that this sequence of effective hydrodynamic theories that I'm going to talk about works at the sort of 10-ish% level.
So compared to lattice, you use physical pion mass.
Well, yeah, I'm going to be talking about the physical pion mass. Yeah.
Okay, thank you.
All right, to estimate how good the logic is. Okay, so, all right, so let's talk about, so again, the main portion of the talk will be to talk about how these superfluid pion modes contribute to the pressure and viscosities of the theory. Okay, so let's quickly sort of give a preview of the results here. Okay, so we're going to talk about how the transport coefficients depend on the pion mass. Okay. So if I look at the bulk viscosity, there will be a piece which is independent of the pion mass. Then there'll be a correction due to the fluid modes, which go like n pi. Okay, and we're going to work out exactly this correction. Similarly, if I look at the shear viscosity, right, the shear viscosity will have a piece which is independent of the pion mass. Then it will actually have a negative correction, meaning so due to the pion. Okay, and finally, if I look at the conductivity, there will be a piece which goes like the leading contribution actually comes from these superfluid modes and goes like 1/n pi, and it's actually divergent. Okay. Okay. And finally, there will be a finite piece which is independent of n pi. So certainly these chiral superfluid modes will be very, very important for discussing the conductivity, all right, of the plasma near TC. Okay, so maybe one important point here is the contribution, these contributions are all proportional to the square root of the quark mass, okay? And this, so it's non-analytic in the quark mass. And this non-analytic structure of these things comes from hydrodynamic loops. So if you know as a long time tail in hydrodynamics, okay, the calculation here is very, very similar to the hydrodynamic long time tails. All right, so let's get forward, start to calculate these corrections. Okay, so let's start with the pressure, okay? So if I talk about the pressure of QCD, right, and I want to calculate what is the contribution of these soft modes, right? Modes which are p of order n pi, that shouldn't have t there. Well, you can write down an effective theory for these soft modes in equilibrium, okay? So there'll be, look at the function, there'll be a hard contribution, which is a contact term, and then there will be a three-dimensional effective theory, which describes how these soft modes propagate in Euclidean theory. And it's kind of looks like chiral perturbation theory in 3D, okay? So there's going to be a Lagrangian. The parameter has the decay constant, which is a function of temperature, and the decay constant and the mass, okay, which describes how these pion modes propagate in the theory. Okay, so for small phase, okay, so U is the matrix of chiral perturbation. Small phase. When you expand it, you get just a simple scalar field with the pion fluctuations here. Okay, you can use that Lagrangian, right, and then you can calculate the pressure due to the soft pions, and you'll get a piece which is coming from the hard modes, and then from this effective Lagrangian, you'll get a piece which goes like T times m pi cubed. Okay, so it goes like m quark to the 3/2. Okay, so somehow the effective Lagrangian sums all these non-analytic terms in the quark mass to the pressure, and so somehow real-time analog of that is what we're going to be trying. Spatial pi decay constant and the screening mass, right? They all have a very universal dependence near the critical point. Okay, so for instance, f squared m squared goes like mq side by side, which goes like mq to the t to the power beta. Beta is a critical exponent. And similarly, f squared goes like t to the power nu, where again, this is the critical exponents of the O4 critical point. So, and beyond just proportionalities and scalings, actually all of the parameters, f squared and the screening mass, m squared, can actually be determined on the lattice with high precision. So if there's enough effort, and I believe there is now and will, okay, and I believe there is now, eventually people will know these parameters with very high precision. And since they will appear in the calculations I'm going to describe, okay, that's useful to know, right? That eventually, right now they're just parameters, but eventually they're going to be real numbers, okay? And certainly the scalings of these parameters are already known. Okay, so let's see what that does. Now let's move from Euclidean. So now we're moving from pressure to hydrodynamics. Okay, so the pressure in the presence of this extra phase, the pion, takes this form just from the previous slide. So you go back, look here at my pressure. Okay, so there's a pressure from all the hard modes. Then there's a pressure contribution from this extra scalars that are running around pion phases. Okay, and now given this pressure, you want to compute the appropriate hydrodynamic theory. Okay, so there's sort of formalism to do that. Okay, so once you know sort of the pressure, at least at ideal hydro level, okay, if you view this pressure as a kind of effective action, then if you vary the effective action with respect to the metric tensor, you can get the stress tensor that you're supposed to use in hydrodynamics. And if you just take this pressure and vary it with respect to the metric, you get usual piece, okay, and then some extra pieces which come from the couplings of these scalars to the pressure, to the normal pieces, okay. Here, P phi, and it's a little bit too compact the notation. P phi is this whole thing, and it also has the Goldstones running around. And E phi is the Legendre transform of this, so it also has the Goldstones running around. Okay. Similarly, if you take this effective pressure and you couple it to a background gauge field, okay, you can find the isovector axial current. Okay, that probably should have a hat on it. Okay. And you find basically that the current has some normal piece, normal isovector current, and sort of superfluid-like current, which comes from this coupling of the scalar to the other modes. Okay, so in addition, if you were to extend the formalism, okay, first of all, by including this mass term, you'll find that the isovector current is not exactly conserved, but it's partially conserved. So that's the partially conserved axial current. Okay. And you also find what's known as the Josephson constraint, which relates the time derivative of the phase to the axial chemical potential. So, good. So, questions? Can I pause here?
The bulk viscosity?
What's that? So it's just ideal hydro that you get.
It's ideal.
This.
Okay.
Right. And now in the next step, we're going to add just because we're getting it from an action, right? here's the action. We're varying the action, right? And we're getting the stress tensor and its contribution, okay, superfluid contribution, and so forth.
Right.
Okay. All right. So, all right. So, first approximation doesn't look too bad. Kind of have hydro coupled to some extra pions, right? Some parameters, which, you know, as I said, like the equation of state, could be gotten from the lattice. Okay. Right. Like this m squared, this f squared. Okay. So let me just spend just a few seconds on this Josephson constraint. Like, what is that? So it says that the time derivative of the phase is the chemical potential. So where does that come from? Okay. So here's the story. So, you know, the Josephson constraint. Well, you see, we're developing a VEV. The VEV is side by side, and it should be stable under the time evolution, right? And so that means, so that here's the phase. The phase U is related to the chemical potential, okay? So here's the side by side. And it's stationary under the time evolution. So if I look at what does that mean? It means that side by side needs to commute with the grand partition function, okay, the Hamiltonian minus mu n, okay? So the Hamiltonian, of course, generates the time derivatives, and this mu q, you know, causes rotations of this field sigma. And so if you look at the transformation properties, okay, you find that ultimately, you have to one line of algebra, okay, you find that the derivative of the phase, which comes from the first term, is equal to these chemical potentials, okay, which is the second terms. Okay, and if you were to linearize this form, you find what the Josephson constraint, okay, that says that the time derivative of the phase is equal to the axial chemical potential. All right, so good. All right, so let's now we've sort of reviewed the ideal theory, okay, which again sort of is just ordinary hydro coupled to some Goldstones. We can start adding viscous corrections to these terms, right? And let's start writing those down. Okay, so let's start looking at the dissipative corrections to the equations of motion. Okay, so first let's write them down. So you have this partial conservation of axial charge. That's this term. Okay, and then you have the Josephson constraint, which says that the time derivative of the phase is the chemical potential. Now, okay, so now these are, so to say, the ideal equations of motion. Now you start expanding in gradients. Okay, so the first term would be the ideal piece. That's the gradient of phase. And now you have a correction which is called the axial conductivity. Okay, and let's just count derivatives. So the first term has one derivative. The second term has one derivative of the chemical potential, but the chemical potential is the time derivative of phase, so that's like two derivatives. Okay, it's one derivative higher. Okay, and now similarly, the Josephson constraint. Okay, the Josephson constraint at ideal order just says the time derivative of the phase is the chemical potential, and now you can have higher order derivative corrections to this Josephson constraint, viscous corrections. So yeah, so that was all written down here. So by Son and Stepanov back in group 2, we did a little bit because we analyzed the entropy production, and then we found additional constraints which come from requiring that entropy production be positive, and we found actually that those two parameters, this kappa 2 and kappa 1, have to have the same coefficient, and basically now we have one less parameter, which is called the axial conductivity. Okay, and what we call zeta 2 for reasons to read the paper. Okay, okay, so that's viscous hydro in this case. Now, of course, once you're adding dissipation, you have to add noises, and by analyzing the production of entropy, you can fix the variance of the noises and relate them to the dissipative parameters. In particular, you know, the derivative, the variance of this noise has to be related to the axial conductivity, okay? the variance of this scalar noise has to be related to zeta 2. All right. So, okay, so now we actually have equations of motion. We have a couple of stochastic equations of motion which describe how the pions evolve. Let's analyze it a little bit and discuss what it's about. Okay. All right. So first thing you would do is look at the linearize the equations of motion and find the dispersion curve. Okay. So linearizing the equations of motion, you find basically that a given wave, okay, first without the noise, will just decay over time, okay, with a damping rate and a dispersion curve, right? The dispersion curve, right, takes this form here. So it has some v naught squared, the pion velocity, times q squared plus m squared, like relativistic form similarly. But it's a little bit different because this v naught squared sits out in front, okay? And it's determined by the parameters of the ideal theory, okay? So in particular, the f squared divided by chi hat, the k constant divided by the susceptibility is the pion velocity. And as I said, we know how these parameters depend on as you go near TC. Okay, so we'll talk about that a little bit later. Now let's look at the damping rate. So the damping rate depends on the two of the pion field, depends on the two dissipative parameters of the theory, zeta 2 and sigma a. Okay, and I've sort of regrouped them here. So the damping rate of the pion goes like the axial charge conductivity. Whoops, I think I'm missing a chi hat. Okay, never mind. Yeah, I'm sorry, I'm missing chi hat. Anyway, okay. So the damping rate has one piece which goes by q squared. That's the axial charge diffusion coefficient. Okay, and one piece that depends on m squared. That's what I was calling it the axial charge damping coefficient. All right. So we sort of have this picture now of pions, which have their dispersion curve, which are determined by the ideal piece, okay, and a damping rate, which are determined by the two dissipative parameters of the superfluid theory. Now, let's just interpret this pion velocity. I'd like to spend just a second to interpret the pion velocity. Yeah, so now if I look at the pion velocity, so the equation of motion for the pion, when you write it out in linearized form, looks like a scalar equation. Okay, so the conservation of axial charge says scalar wave equation for the pion, and it has a piece with the conservation of axial charge and a divergence of the superfluid current. Okay, now this conserved charge we sort of talked about, it is the total axial charge. It has some piece which comes from the pion field and some normal component, some super component, and some, say, normal component, which is all the other higher hydronic states. Okay, and so if you actually look at what the pion velocity is, right, it's sort of say this super component is proportional to x squared, okay, divided by the total axial charge susceptibility. So it's sort of say the ratio between how much is in the superfluid mode and how much is in the super plus normal, okay? And so the pion velocity near TC is somehow a measure, right, of exactly how much is in the superfluid modes and how much is in the normal modes. And, as you would expect, near TC, almost everything is in the normal mode, and the pion velocity then approaches 0. Okay. So anyway, so let's press on now. So here's the overall picture now. We have basically hydrodynamics, which is weakly out of equilibrium, and maybe you drive it in some way. I mean, that's the simplest way to keep it out of equilibrium, is to drive it with some external force, say gravity. Okay, and then these hydrodynamic modes are out of equilibrium, And that makes these superfluid modes out of equilibrium and hard modes also out of equilibrium, right? Now, if I look at very long distances, the degree to which these are out of equilibrium, which is determined by the dissipative parameters of the superfluid theory, influences the transport coefficients of the long wavelength theory, okay? And so that's basically the strategy. We're going to drive the system with some external force. Now we're going to calculate how these modes are driven out of equilibrium. We have a stochastic hydrodynamic theory for that. And then we're going to calculate their contribution to the stress tensor, right? And their contribution to the stress tensor then will determine the contribution of the superfluid modes to the dissipative parameters of the full theory. Okay, so you want to describe how these modes are driven out of equilibrium. You have that right hydrodynamic theory. So what you could do is develop a set of kinetic equations from the hydrodynamic equations for these superfluid modes. Okay. Alternatively, if you prefer it, you could like integrate out these superfluid loops, okay, and ask how they change the stress tensor. So we did it both ways in the paper. You can either integrate out the superfluid loop, or you can develop the kinetic theory. I'm going to talk about the kinetic theory here, okay, because I think it's much more useful for heavy ion collisions going forward. Okay, okay, so let's, how do you develop, what we're trying to do is ask how these modes are driven out of equilibrium. How do they evolve? Okay, what's their phase space density of these modes and how they evolve? So here's what our equations look like, okay? So basically we have a set of linearized equations for the phase and the axial charge. And the equations of motion look like some matrix versions of Brownian motion, okay? So that d phi dt is some ideal piece, and then there's some damping piece and some noise piece, and of course the noise is related to the damping piece. So what you would do to analyze this stochastic set of matrix equations is you would break it up into the eigenmodes, the system into the eigenmodes, and analyze how the different pieces evolve, okay? And if you do look at the eigenmodes of the system, you do see that they are the sort of second sound. They are the modes that we were describing earlier. Okay. Now, so these eigenmodes are the phi plus minus. Okay, so now I want to ask, how does the phase space density of these modes change under this stochastic evolution? Right? So the thing you want to look at is the Wigner density or the Wigner transform of this eigenmodes. Okay, so this is, the object that you develop. Okay, and now you ask, you have the equations of motion, stochastic equations of motion, and so you can determine using those stochastic equations of motion how this phase space density evolves in time. Okay, and I'm not going to go through the details of that derivation, but it's plausible at least that this Wigner density should follow, kind of Boltzmann equation. And indeed, after analyzing the equations of motion, you do find just exactly this Boltzmann equation. So here's how the phase space density evolves, the streaming term. And you see here basically streaming term, and here's the relaxation towards equilibrium. Okay, it's kind of embarrassingly simple Boltzmann equation. Looks almost like a relaxation time approximation. The only difference would be that the dispersion curve is related to the equilibrium properties of the superfluid theory, and the dissipative parameters, this dA and dm, are related to the transport coefficients, the two transport coefficients, right? Coefficients of the theory. Okay, so somehow the fact that we have an underlying hydrodynamic theory guarantees that this form of the Boltzmann equation on the right-hand side, the collision integral, is extremely simple. Okay, can't be more complicated. And the dispersion curve, right, is given by kind of an effect Hamiltonian that the particles move around in. Okay, so the particles, the pions, will basically feel this effective metric, which is set by the fluid velocity and the pion velocity. Okay, and they sort of evolve in this effective metric. Okay, so in principle, and this is something to be said here, you know, this Boltzmann equation for the soft pions can be simulated, right, in a heavy ion collision. And if you know how these parameters change in temperature, and as I said, you could get that from the lattice, okay, then you can simulate how these soft pions are emitted from the sort of, say, phase boundary of the heavy ion collisions using this thing, okay? So, and there's a lot of reasons to be excited about that, right? Because, so this is speculation, you know? If you look at how well we all think that hydrodynamics works well at describing heavy ion collisions. But if you look at the soft pions in heavy ion collisions, they're totally off. All hydrodynamic codes miss them completely, like 50%, 60% off, okay? And that's including all resonance decays and everything. And there doesn't seem any real progress towards fixing that, okay? And I would suggest that probably that's because they are not including how the dispersion curve changes near the critical point, meaning that this energy goes to zero. Okay, good. So that's hopefully work in the future and sort of describe that in the future. Okay, now that we have this Boltzmann equation, we can sort of ask how does these soft pion modes change the transport coefficients. Okay, so it's actually kind of standard procedure now. Okay, the mode distribution, here's the form of the Boltzmann equation, sort of has if I drive it with some, you know, driving term, okay, this driving term will tend to drive the system out of equilibrium. And then there'll be another term, the collision kernel of the Boltzmann equation. It tends to relax the distribution to equilibrium. And then once you've determined how this mode distribution, how far it is from equilibrium, you can calculate how this mode distribution changes the stress tensor. Okay? And okay, so we have an explicit expression for the stress tensor. So there's this superfluid contribution, and this pion mode distribution will contribute to that superfluid stress. Okay, so if you have something like this, if you know the 2-point functions of the scalar field, okay, this contribution becomes something like this, right? It's an integral over the phase space distribution with Qi, Qj. Okay, so writing it out, you find it kind of somewhat unusual forming. So say the pion distribution has a, you know, the stress tensor in the presence of these soft pion fields is given by this formula. Okay, so okay, so now we're sort of ready to do it. Okay, so again, the steps would be drive the system out of equilibrium, calculate the viscous correction, the phase space distribution. Finally, integrate over the viscous correction and determine the viscous corrections for the stress tensor. Okay, so here's our final expressions then for instance, the bulk viscosity. So the bulk viscosity would have some piece in the chiral limit. Then it would have some contribution from the soft pions. Okay, and these contributions depend on the velocity of the pion, okay, which again could be given from lattice, and also, you know, and the mass of the pion. And so you can, you know, with a couple integrals, you find the first correction due to the pion mass to this bulk viscosity. So you sort of get some piece here, which looks complicated. Okay, there's a bunch of different terms there. Let me just sort of step through them. Okay, most of the terms here are this involve this pion mass and the pion velocity. There's also the axial charge diffusion coefficient sitting there, and the ratio between the axial charge damping coefficient and the axial charge diffusion coefficient. Okay, so it looks a bit complicated. If you look at all of them, right, you get final formulas. Okay, so this records, the first correction due to these fluctuating phase and pion mass to the transport coefficients, the bulk viscosity of QCD, shear viscosity, and the conductivity. Okay, so all right, so we just got to see what was advertised in the beginning. The bulk viscosity gets a correction like 1 power of the pion mass. Shear viscosity gets a negative correction like 1 power of the pion mass. The conductivity goes like 1 over the pion mass. Maybe we could just reflect here why it is that the conductivity goes like 1 over the pion mass. So it's actually really simple. So the pion is a Goldstone boson, and as such, it barely ever scatters. In the limit that the mass goes to 0, it really never scatters. It's kind of a free particle, in which case, that is a very efficient way to transport charge, okay? And therefore, it's natural that the isospin conductivity should go to infinity in the limit of the Carver limit. Okay, so now let's go and ask, what happens near the critical point? Okay, so I have these formulas. What happens to them near the critical point? How do they behave? So here's the formula. So first of all, near the critical point, the mass term is not important, and so you get already simpler formulas. Okay, that's good, right? So still looks a bit complicated, but the shear viscosity is totally variable. It goes like the mass, the screening mass of the pion, and the diffusion coefficient. These terms here are all static quantities, meaning that they're given by static O4 universalities. So we know how all of those quantities depend near the O4 critical point. So in there, the only thing we maybe a little more complicated is this axial charge diffusion coefficient, which is not given by static properties of the O4 critical point. Nevertheless, you can determine how this diffusion coefficient depends, right? So near TC, the pion damping rate is the same as the sigma damping rate, okay? And the sigma damping rate, so the pion damping rate goes like that, is proportional to the axial charge diffusion coefficient. And the sigma damping rate, right, is governed by, again, universality. Okay, so using the dynamic universality of the O4 critical point, the sigma damping rate goes like m sigma to the power z, where z is d over 2, 3/2. Okay, so we actually know how near the critical point, both how all of these terms depend on temperature, and we also know how the axial charge diffusion coefficient depends on temperature near the critical point. And so you could substitute those in there and determine how these parameters depend. Okay, so here's kind of our little bit of our results here. Now what you find is that the bulk viscosity, okay, grows like a relatively large power of the temperature, okay, near the critical point. So you see here this T to the 4th, okay, so you get T, T is the reduced temperature, T minus TC, okay. So what you see is that the bulk viscosity grows like T to the minus 3.81, so it grows rapidly, okay. Similarly, the shear viscosity has a very slow growth. It grows like T 0.19, okay, probably too small to be seen in a heavy ion collision. And finally, the soft pion contribution to the charge diffusion actually sort of dominates the result. And it sort of falls as you approach the critical point, as T to the 0.55. Okay, so that's kind of the results here, you have sort of appropriate scaling behavior of these things. And yeah, that's kind of the result. So there is a part 2, but I think we're kind of already out of time. But let me just jump to the results. So in chiral perturbation theory, you could calculate these parameters, and we did that. And you could calculate how the diffusion coefficient, axial charge diffusion coefficient, what is its form and so forth, and what is the axial charge damping coefficient. But I'll skip that today. Okay, so it's 40 minutes, right? So we'll stop there. And,
no, you have 10 more minutes still.
10 more minutes. Okay.
Yeah.
So if I give it just a tiny bit hint about the chiral perturbation theory, at least the setup. So, so here was this formulas, right? So we talked about this hydrodynamic theory is valid, okay? Now, if you have an underlying microscopic theory, which respects chiral symmetry, then you could go use that microscopic theory to calculate the transport coefficients. Okay, so we kind of wanted to do that, just to understand a little bit more from a microscopic perspective what we're talking about, okay? And so we started to calculate how the parameters depend in chiral perturbation theory. So if you have microscopic Lagrangian, so now we're working in a very specific regime, which is not the real world, okay? So we're assuming that the pion is the lightest parameter. It's much less than the temperature, and it's much less than the cutoff, okay? Then you have a very specific microscopic Lagrangian, which will have a superfluid behavior long distances, okay? And then we have here this formula that we derived using hydrodynamics for the shear and the bulk viscosity. In particular, the bulk viscosity depends very simply on this dissipative parameters of the superfluid theory, dA and dN. So, so we were kind of interested in computing, how do you compute those? So it's ended up being way more complicated than we anticipated, okay? So if you look at chiral perturbation theory and you start to analyze it in this regime, okay, there are hard modes, which are not superfluid modes, with P of order the temperature. There are soft pions, okay, with P, where the wavelength number is comparable to the spacing between collisions. Okay. Here I've defined F bar, which is the decay constant divided by temperature. So it's a very large number. This is very soft. Okay. And finally, you have ultra soft pions or hydrodynamic pions, where P is of order M pi. So basically, our goal, or the program in the heavy ion in the kinetic in chiral perturbation theory, would be to integrate out the hard modes, integrate out the soft modes, and be left with a hydrodynamic theory of ultra soft pion modes. Okay. So here's kind of artist's picture of what I view chiral perturbation theory in this regime like. Okay, so you have very long wavelength pions, which are my superfluid nodes. Inside this chiral perturbation theory, you have pions scattering, hard pions, which are scattering all the time, but they don't really influence, they just sort of modify these parameters a little bit. And then you have longer wavelengths where the green lines are comparable to the spacing between collisions. Okay, so that was, anyway, the setup. So let me just say, since time is short, let me just say a little bit how it goes, okay? So you have here basically this equation of motion from your superfluid theory that you say, okay, the divergence of the axial charge is related to the dissipation rate. And so if I look at this equation of motion, I need to compute basically the imaginary part of the retarded self-energy of the soft, very ultra-soft pion fields. Okay, so so from this thing, this equation of motion, you can identify this axial charge diffusion coefficient from the retarded self-energy of the soft pion fields, which is not surprising. And so if you're naive, and we started out being naive, you think that I could just kind of compute this loop and calculate the imaginary part, and that would determine the axial charge diffusion coefficient. Okay, so now that's basically right, okay, but it turned out to require a lot of resummation, as is typical with hydrodynamics. So whenever you have hydrodynamics, okay, you have lots of scatterings, okay, and these graphs just describe one scattering, okay, and so so it's typical you'll need a lot of resummation, and this won't work per se. So anyway, so I don't have time to really go over, but let me just say that one of the issues, okay, so in particular, if I look at this collision process, the kinematics are very, very specific, okay, so you have one hard momentum line, and now you're going to spit out two hard momentum lines and a soft pion. And now look at the energy, the formation time of this process. Okay, look at the energy difference between these rates. Okay, so the energy difference between the final state and the initial state is okay. It's given by this difference in energies. This thing is so soft. Okay, it's ultra soft, so you can ignore it. And now if I look at the energy of difference between these states, the pions are essentially outgoing collinear, and you see that this energy difference between these states is comparable to the spacing between collisions. Okay, and so the collisional width of these lines can't be ignored in the scattering process. And in addition to sort of say 1 to 2, in addition to say 2 to 2 scattering processes in the pion gas, things like 1 to 3 are also perfectly okay. Okay, so that's essentially one of the problems that we arose here, is that the collision duration is sort of say comparable to the width. Okay, and then you have to include sort of say 1 to 3 processes. Okay, so now I will not go through the resummation of that. We spent some time doing that, and we sort of do get the sort of final result. So we basically find that calculated the axial charge diffusion rate and the damping coefficient. So this diffusion coefficient, it actually looks like a typical scattering rate. I mean, there's nothing special about it. It's sort of say of order the typical collisions in the gas. Okay. There's a log, which is a great source of difficulty, but nevertheless, okay, it still doesn't change the essential feature that the axial charge diffusion coefficient is of order the typical scattering rate. Good. I guess that maybe the only thing would be is that this logarithm, which is called the Carver log, is screened by the mean free path. And so we finally get that the leading order bulk viscosity and conductivity in chiral perturbation theory have these somewhat unusual dependence on m pi. Okay, which I would say is almost, without developing some set of effective theories, is essentially very difficult to compute otherwise. Okay, thanks.